All right, I apologize, my camera cut off. So f of x equals 1/2 x plus 3. And so what I've done is I've substituted in each of the x values. If I substitute in -4, I will have 1/2 times -4 plus 3. Half of 4 is 2, and a negative times a positive is a negative. And -2 plus 3 is 1. And that point, -4, negative or +1, is -4, +1 right here. Okay, next I would substitute in -2. -2, 1/2 times -2 will give me -1 plus 3. -1 plus 3 is 2, and so 2 will show up as right here, and -2 is a point on my graph, -2, 2. Similarly, if I substitute in 0 right here, I'll just get 3. If I substitute in 2, half of 2 is 1, 1 plus 3 is 4, and finally, half of 4 is 2, 2 plus 3 is 5, or once you see that it's going up by the same amount each time, you can just fill in your table. And then it says to use the table from step 1 to create a table of values for f inverse of x. So we don't know this function, but what we do know is this relationship. The relationship is that the domain, or the x values, will become the y values of the inverse function, and the range of the original function, the y values, will become the x values. So I simply switch these. So I should have 1, 2, 3, 4, 5 for my domain, and -4, -2, 0, 2, and 4 for my range. And so they've graphed that function. And note that you can see that symmetry happening. Here's that line y equals x going directly through the origin, and I see that they're symmetric. So another way to graph, if you don't want to use a table, is that you could count catty-corner or diagonally to find these points. Some students are very visual. For example, this point is 2.5 units from the line y equals x. That means if I continue a half, 1, 2, I will have a point on the inverse function. And this point is exactly 1, 2 units diagonally. That means I'll have a 1, 2, another point on the inverse function 2 units diagonally across. All right. And it says, since both f of x and f inverse of x are linear functions, the domain of both is all real numbers. Likewise, the range of f of x and f inverse is all real numbers. So again, anytime we have linear functions, there will be no restrictions. Okay, it says to graph each function on the coordinate plane, then use symmetry or a table of ordered pairs to graph the inverse function. Determine the domain and range of each. All right, so my first function is f of x equals -2x plus 3, so my slope is -2, right? -2 over 1 is my slope, which means I can go left and right, down and right, or I can go up and left, either one. And I'm going to start at +3 on the y-axis, so I've done that. I started at 1, 2, 3 on the y-axis, and I've gone down 2 and right 1, down 2, right 1, down 2, right 1. Or I could go up to left 1, up to left 1, and so on, and sketch in your line. Now the inverse function, it says you can use either symmetry or a table of ordered pairs. So I'm going to do it first with symmetry. So symmetry means I'm using the line y equals x. And so just to make sure that my graph is really accurate, I'm going to make sure I put as many points as I can, and I'm going to sketch in this line y equals x. And then I can count diagonally from the line that I've graphed, f of x, to this dashed line. So I'm going to count from here. I go down, I go over diagonally 1.5. So diagonally I'll go a half and then 1. There should be a point right there. I can do the same thing with this point. This is diagonally 1, 2, 3 units. So there'll be a point 1, 2, 3 units. Similarly, this point won't move. I can also use this point. It's 1.5 units diagonally, so a half and then 1 unit diagonally. And this point is 1, 2, 3 units. So this point will be 1, 2, 3 units. And now I have enough points to graph my line. So that is using symmetry to graph f inverse of x. Now, some students who aren't very visual, they prefer the table method. And so the table method is that I would identify points on my original line. So for f of x, I will identify some domain and range values, ordered pairs. So for example, the point -1, 1, 2, 3, 4, 5. So -1, 5. The point 0, 1, 2, 3, 0, 3. So this is like your x and your y values, right? The point 1, 1. The point the point 1, 2, 3, 0. I'm sorry, that's the wrong line. The point 1, 2, -1. And the point, this would be 1, 2, 3, -1, 2, 3, 3, -3. Now to graph f inverse of x, all I need to do is switch these values, these domain and range values. And so my x values and my y values, right, will switch. My domains and my ranges will flip-flop. So these will become my y values, and these will become my x values. So I would have the point 5, -1, and 3, 0, and 1, 1, and -1, 2, and -3, 3. Now we can verify if that happened by looking at our graph. So I should have 5, -1, 5, -1, yes I do, 3, 0, 3, 0, 1, 1, 1, 1, -1, 2, and -3, 3. So you get to pick which method you prefer. I do find most students prefer this method, using the graph, but if you prefer to use the table, you may. All right, let's do the second example, the try these B. And so this one I'm going to do on a separate sheet of paper. So try these B, my function is f of x equals x plus 6 over 3. I'll change this into slope-intercept form. Y equals, this is a 1/3, x plus 6 over 3 is 2. And now I can create a table of values, or I can graph using slope-intercept form. So I don't have graph paper in here, so I am going to go over to another spot where I can use some graph paper. Let's see. I'm going to use this page right here so I can use that graph paper. I want my graph to be accurate, and without lattice points, it's really hard to graph this way. Okay, so my y-intercept is at 2, positive 2, so right here, and my slope is up 1/3, so it's going to go up, up 1 over 3, so up 1, right 3, or I can go down and left, so up 1 over 3, or down and left, and I'm going to sketch my graph. Then I'll graph in my line y equals x, which remember, y equals x is the diagonal line going through the origin. And I can, if I want to, just use symmetry to graph. So I can go diagonally from this point, I'd go 1, 2. That means there'll be a point 1, 2 units this direction. This is 1, so I'll go 1 unit. This point is on the line of symmetry, so it won't move. This point is 1 unit this direction, so there'll be a point 1 unit this direction. And then I can sketch in y equals f of x. Or sorry, not y equals, f inverse of x. So there's f inverse, and here is f of x. Or I could have created a table. So if I created a table, those values for my original function, right, x and f of x, I have the point negative 1, 2, 3, 1. So negative 3, 1. I have the point 0, 2, 0, 2. I have the point 3, comma 3. And I have the point, that would be 3, 4, 5, 6, comma 1, 2, 3, 4, 6, 4. Then what would happen is that my x values would become my y values, and my y values would become my x values. So these would be my new x values. These would be my new y values. 1, negative 3, 2, 0, 3, 3, and 4, 6. And we can check that out right here. Let's see if on the gold line, if that's what we got. We have 1, negative 3. So 1, negative 3. Yes. We have 2, comma 0. Yes. We have 3, 3, and 4, comma 6. All right, so you get to pick which method you like. And again, they did ask to identify the domain and range. Since these are linear functions, the domain of both is all reals, and the range of both is all reals, or from negative infinity to positive infinity. Okay, so let's flip it back over to check your understanding. Attend to precision. Suppose that the domain of f of x equals 1/2 x plus 3. In example A was restricted to where x is greater than or equal to 0. What would be the domain and range of f inverse of x? Explain your reasoning. All right, well, let's go back and look at that example. In example A, it says, suppose that the domain was restricted to where x is greater than 0, and that's for our original function, right? So we're going to look at our original function, f of x, which is this line, and we're going to see what would happen if our domain were restricted to where x was greater than or equal to 0. So where x is greater than or equal to 0, well, then the only portion of our line that we would really have is this portion from here this way. And the rest of this would not exist. So if that were to happen, it says, what would happen to the domain and range of f inverse of x? Well, let's look at the domain here of this original function. So the domain of this function is x is greater than or equal to 0. So that's the domain. The range of the function goes from 3 to infinity. So x would be, y would have to be greater than or equal to 3. I'll say that again, right? The range is the y values. The lowest y value is 3, and it goes on forever, upward. So our range would be from 3 on. So in theory, what should happen then is that our domain and range of the inverse function, the range of the original will be my domain. So x will be greater than or equal to 3. And the range would be that y is greater than or equal to 0. So let's check that out and see if that happened. So on my inverse function, which is this guy right here, my smallest x value to the left, as far as I can go, is at 3, and it's going on to the right forever. And my smallest y value is at 0. So again, x, we have on the x-axis 3, and on the y-axis, or on the x-axis we have 3, and on the y-axis we have 0, which is exactly what happened. All right, it says graph each function and its inverse function. I am going to let you guys attempt these, right? You should try these and see if you get a graph that's a reflection of itself across that line y equals x. And it says, what is the relationship between these two graphs with respect to the line y equals x? So the relationship between a graph a function, and its inverse function is that they are symmetric at the line y equals x. All right, let's take a look at the next page, which is page 99. All right, on page 99, now we're going to start graphing quadratics that may have restrictions on the domain. So I think I'm going to break that into a separate video. I'm going to stop the notes right here, and we will continue with this in the next lesson. All right, thank you.